Good afternoon, everyone. So we are discussing about properties of Fourier transform and problems based on Fourier transform properties. Okay. So linearity property, uh, time shifting property, time reversal property, frequency shifting property. Okay. So these are the properties we completed, and simultaneously we have solved few problems also as an example of each and every properties. How to use those properties and all. Next one, time scaling property. So time scaling property says that if the Fourier transform of x of t is x of j omega, then Fourier transform of x of at, if the signal is scaled by the factor a, the result would be equal to 1 divided by modulus a, x of j omega by e. Okay. So this is called as time scaling property. Next one, differentiation in time domain. Differentiation is time domain property. It says x of t Fourier transform x of j omega. If d by dt of x of t, if you differentiate x of t with respect to t and then find the Fourier transform, that should be equal to j omega into x of j omega. Okay. So already I told you I'll give the proof for each and every property separately as a handwritten material to you. Now remember all the properties and understand how to solve the problems using properties. D by dt of x of t. Then you find the Fourier transform. The result should be equal to j omega dot x of j omega. X of j omega is Fourier transform of x of t. Or in general, differentiation of x of n in the order of n. Okay, then result would be equal to j omega power n dot x of j omega. So this is differentiation in time domain. Differentiation in frequency domain property. If x of t equal to x of j omega, then t dot x of t multiplied with x of t. If you find Fourier transform now, the result will be equal to j times of d by d omega of x of j omega. So this property called as differentiation in frequency domain. Now, two problems. Determine the Fourier transform of the following signal using properties of Fourier transform. First problem, x of t equal to t dot e power minus at into ut. Okay. So how to solve it? X of t, x of j omega, right? T dot x of t, then result will be equal to j times of d by d omega of x of omega. Differentiation in frequency domain property. So based on this property, solve this problem. So problem first one. E power minus at dot u of t. This is the first problem we have solved in Fourier transform. E power minus at ut. The result is 1 divided by a plus j omega. E power minus at ut, the result is 1 divided by a plus j omega. Now we have to calculate Fourier transform of, or we have to find the Fourier transform of t times of e power minus at ut. Okay, if this entire term consider as x of t, this entire term consider as x of j omega. If x of t Fourier transform x of j omega, Fourier transform of t times of x of t. Now Fourier transform of t times of x of t, then the result will be equal to j d by d omega of x of j omega. Okay. So j d by d omega of x of j omega. Okay. So Fourier transform of t dot x of t. Particularly in this example, t dot e power minus at u of t. E power minus at u of t. The result will be equal to j times of d by d omega of x of j omega 1 divided by a plus j omega. Okay. So differentiation u by v formula, u divided by v formula. So let's j u by v square v du a plus j omega du constant 0 minus u dv. So a constant j omega, j is the remaining part. Okay. So the answer is j square value minus 1. This minus will be cancelled. So the result is 1 divided by a plus j omega square. 1 divided by a plus j omega square. Okay. So this is another formula actually. E power minus at ut t into e power minus at ut. E power minus at ut Fourier transform formula 1 divided by a plus j omega. T e power minus at ut, the Fourier transform formula 1 divided by a plus j omega square. So remember this formula. Later we will be using this formula while solving the inverse Fourier transform with the help of partial fractional method. Okay. Just applying the property, that's it. Second problem, t cos 2t. Second problem, x of t equal to t cos 2t. Okay. So what the property says, x of t Fourier transform x of j omega. Then if you find t times of x of t Fourier transform, result should be equal to j into d by d omega of x of j omega. Correct? So in this example, consider your cos 2t is your x of t. Cos 2t is your x of t. What is the Fourier transform of cos t? So we have solved already, right? In the beginning of the classes. Sin t, cos t. X of t equal to cos omega naught t. X of t equal to cos omega naught t. Fourier transform result is pi del of omega minus omega naught plus del of omega plus omega naught. So that is the result for cos 2t. So cos 2t Fourier transform pi del of omega minus omega naught. Here omega naught 2 plus del of omega plus 2. So this is x of t. This is x of j omega. But we have to find out Fourier transform of t times of x of t. Then the result should be equal to j d by d omega of x of j omega. Okay. Now, as per the properties, Fourier transform of t times of cos 2t. Fourier transform of t times of cos 2t. J d by d omega of pi del of omega minus 2 plus or if you use common bracket, I is not real. Del of omega plus 2. That's it. Stop the answer up to this particular step. Okay, so these two problems is an example for in frequency domain. Differentiation is frequency domain, right? So I'll give you one example for time domain. D by dt of x of t. Okay. And no examples are available. Okay. Right. So we'll move on to next property. Sorry for the interruption. Can you hear me? In full rain here actually. Is my voice audible? Please respond, anybody.
Sir.
So differentiation frequency domain and some examples using that property. Next property.
Screen share చేయలేదు సార్.
Next property number 8. Time integration property. Okay. So Fourier transform of x of t. Let's say x of j omega. So then Fourier transform of integration minus infinite to tau x of tau d tau. That result would be equal to 1 by j omega x of j omega plus pi x of 0 del of omega. If initial values are 0, then the result will be equal to x of j omega divided by j omega. Please remember this. Fourier transform of integration of x of t dt. Result is x of j omega divided by j omega. Fourier transform of differentiation of x of t. J omega times of x of j omega. Remember this, okay? Fourier transform of d by dt of x of t, j omega into x of j omega. Fourier transform of t dt. Result is x of j omega divided by j omega. So this is another property. Property number 8. So property number 9. It's very important property for solving the problem. Duality property, or otherwise called as duality theorem. Duality property or duality theorem. It says that if x of t Fourier transform is x of j omega, then Fourier transform of x of t equal to x of j omega. So duality principle says that Fourier transform of x of t. Please understand, I am using small x for time domain representation, capital X for frequency representation. Small x of t, capital X of j omega. Now, Fourier transform of capital X of t. What do you mean? From this answer, all this j omega replaced by t. Now, if we find the Fourier transform of this particular answer, the result should be equal to 2 pi times of small x. This x, this t is replaced by minus j omega. This theorem is very important for solving the problem. X of t, capital X of j omega. If you find Fourier transform of capital X of t, that meaning whatever answer we got here, in this answer, that Fourier transform of x of t, some signal, all the j omega replaced by t. Then the result is equal to 2 pi times of this x of this t replaced by minus j omega. So with some example, you can understand this, how to solve the problem using duality theorem or duality principles. Okay. So one problem will solve. Example, find the Fourier transform of the signal x of t equal to 1 by t. Okay. Find the Fourier transform of the signal x of t equal to 1 by t. Using Fourier transform properties. So remember the formula of Fourier transform of signum function. So we know that Fourier transform of signum function result is 2 divided by j omega. Okay. So we have solved this answer already. Signum function of Fourier transform signum function 2 divided by j omega. Okay. So already we have done it. So these all are fundamental formula. You should remember the formula of Fourier transform of signum function. Now apply the duality principle. X of t. X of t is 1 by t. X of t is 1 by t. Fourier transform. Result is 2 divided by sorry, x of t is signum function. X of t is signum function. We apply the Fourier transform. Result is 2 divided by j omega. Okay. So what is the duality principle says? Then Fourier transform of capital X of t. That is Fourier transform of 2 divided by jt. Fourier transform of 2 by t. J omega replaced by t. Okay. So it should be equal to 2 pi del of 2 pi of x of minus j omega. What is your x of signum function? Signum function of minus j omega. Okay. So now Fourier transform of 2 by t, we got the result. 2 pi signum function of minus j omega. So 1 by t2 is a constant. 1 by t meaning that 2 will go right side. So Fourier transform of 1 by t. Okay. Fourier transform of 1 by t. The 2 will be cancelled. So we will get pi. So even this minus j also we can take outside. Minus j pi signum function of two will be cancelled. Pi signum function of j omega. This is the result. Just take minus outside. Okay. So like this, many problems are there. We can solve using duality theorem. I'll repeat once again. X of t, capital X of j omega. Then duality principle says that if we find Fourier transform of capital X of t, that means all j omega replaced by t. It should be equal to 2 pi times of this term, your result, but the t replaced by minus j omega. So in this example, signum function Fourier transform 2 by j omega. So if we find Fourier transform of x of t, capital X of t, capital X meaning here 2 by j omega replaced by t. That result should be equal to 2 pi times of x of minus j omega. What is x of t? Signum function t. So signum function of this t replaced by minus j omega. Okay, but we need a Fourier transform of 1 by t only. So 2 is a constant. As per linearity principle already we studied. Okay, so this 2 will come outside. So 2 times of f of 1 by t. The 2 goes right side, that it will be cancelled. So result is minus by signum function of j omega. So this property called as duality property. Or duality principle, duality theorem, all are same. Property number 9. So next, property number 10. Convolution property. It's very important property. So what convolution property says? X of t, h of t. Fourier transform of convolution between signal in time domain. this is equal to multiplication of their individual transformation. Okay. Here I mentioned x of t, h of t. You consider any signal, x1 of t, convolution x2 of t, convolution x3 of t. Then if you find Fourier transform, the result is equal to multiplication of their individual Fourier transform. Okay. So this property called as convolution property. Similarly, we have multiplication property. Convolution property meaning Fourier transform of convolution of signals is equal to multiplication of their individual transformation. Okay, so this very important advantages of time domain. So how to get the answer in time domain for this particular x of t convolution with h of t, x of tau, h of t minus tau. Then we have to shift h of t minus tau from minus infinite to infinite and check the integration limit each and every shift. In unit 2 we have done it. Okay, but same thing we can implement in frequency domain. It's very simple. Find Fourier transform of x of t, find Fourier transform of h of t, multiply these two. Now take inverse Fourier transform. This result would be equal to y of j omega. Then if you find the inverse Fourier transform, you will get y of t easily. So the number of computations in frequency domain is very, very less when compared with time domain. So this is one example. What is the application of, what is the advantages of processing the signal in frequency domain? Okay. It reduces the complexity. So I explained in terms of convolution. Similarly, for a complex application, so if we go for the frequency domain processing the signal, so that will be the added advantages. A reduced number of hardwares and computation time. Okay. Next, multiplication property. We'll see the example for convolution property surely. So before that, multiplication property. What multiplication property says? Say for example, x1 of t, x2 of t. Two signals are there. x1 of t multiplied with x2 of t. Now if we find the Fourier transform of this signal, this result would be equal to 1 divided by 2 pi times of convolution of their Fourier transform. Okay. Convolution in time domain, result is multiplication in frequency domain. Convolution theorem. Multiplication properties is multiplication of signal in time domain. The result is equal to convolution of their individual Fourier transform. Okay, so this property called as multiplication properties of Fourier transform. So some more properties are related with complex terms and all. So that's not that much important. The last one is Parseval's theorem. Okay. So this property is very important. Many times I could see in the question paper, state and prove the Parseval's theorem in Fourier transform, Laplace transform, DTFT, Z transform. In all the transformation, it is available. So what's this? What this particular theorem states? We studied the formula to find the energy of the signal. energy equal to minus infinite to infinite modulus x of t square dt. Okay. So this is what we have studied in unit 1. Compute energy of the given signal formula. The same formula, same thing, we can obtain with the help of Fourier transform. That is, energy spectrum of a signal or energy density spectrum with help of Fourier transform 1 by 2 pi minus infinite to infinite integration x of j omega square into d omega. So this is the property. Okay. Energy density spectrum of a signal can be obtained from Fourier transform. The formula is 1 by 2 pi integration modulus x of j omega square d omega. You know what is x of j omega? X of j omega is Fourier transform of x of t. It's called as energy density spectrum. Okay. So proof for this theorem is very simple and also important. So I'll do it here now. So energy equal to minus infinite to infinite modulus x of t square into dt. So this may be represented in terms of complex now system, that is x of t, x star of t. Okay. So already we know that your Fourier transform result in the form of real part plus imaginary part. Now x of t modulus x of t square can be written as x of t multiplication with complex conjugate of x of t. Right. Next, integration minus infinite to infinite x of t and dt, let it be. So we have to write replace this x star of t with some other term. Okay. So what is the formula for inverse Fourier transform? Do you remember? Inverse Fourier transform formula. X of j omega equal to x of t e power minus j omega t dt. Fourier transform of x of t. Inverse Fourier transform of x of j omega, x of t equal to 1 by 2 pi x of j omega e power plus j omega t d omega. With the help of that formula, x of t equal to 1 divided by 2 pi integration minus infinite to infinite x of j omega e power plus j omega t into d omega. So this is inverse Fourier transform, that is x of t. But here complex conjugate of this signal. This entire signal complex conjugate. So if we bring this complex conjugate inside, we will get 1 divided by integration minus infinite to infinite x star of j omega e power minus plus j omega. Now this would become e power minus j omega t into d omega. Okay. So what I did, I replaced x complex conjugate of x of t from inverse Fourier transform. Now rearrange this particular equation. One divided by 2 pi integration minus infinite to infinite x star of j omega. Okay. Now combine all other term minus infinite to infinite x of t e power minus j omega t dt. Combine these all the term together, then d omega. So what is x of t e power minus j omega dt? That is a Fourier transform of x of t. So 1 divided by 2 pi minus infinite to infinite x star of j omega. This term is nothing but Fourier transform of x of t formula represented by x of j omega into d omega. Now this can be written as 1 divided by 2 pi minus infinite to infinite x star of j omega x of omega. X of j omega multiplied with complex conjugate of x of j omega. That can be written as modulus x of j omega square into d omega. Okay. So this is the proof for this particular theorem. Similarly, there is a proof for all the previous 11 properties. Okay. So due to insufficient time, so I'll be giving as a note. Once you read the property, you can easily understand. I'm sure about that. Because similar property available for Laplace transform, DTFT, Fourier series exponential, and Z transform. Okay. So only the notations will be changing. The basic characteristics of each and every properties are same in all the mathematical tool, whatever we are studying in the signals and system. Next. So in between, one student asked me the doubt whether this Fourier transform applicable for periodic signal or not. Yes, Fourier transform applicable for periodic signal also. Anyway, we found sin t cos t, so that is with the help of some fundamental formula. Okay, actually in this particular unit 3, initially we studied Fourier series concept, trigonometric Fourier series, exponential Fourier series concept. How we solve for a given signal. Suppose a signal is given like this. Then we find Fourier series coefficient. This signal can be represented by harmonics of sinusoidal and cosine components in trigonometry. In exponential Fourier series, in some other expression. But anyway, any continuous time periodic signal as well as discrete time periodic signal, that is discrete Fourier series, we don't have in the syllabus. So any periodic signal can be represented by the Fourier representation. Okay, but aperiodic signal analysis not possible with the help of Fourier series. So then we move on to Fourier transform. So far, whatever problem we discussed, except the sin t cos t, all the signals are aperiodic signal only. Okay, please remember this. We are discussing about all aperiodic signal only so far. So is there formula to compute Fourier transform of a periodic signal? The formula is available, but we have to derive it. We should not use the same formula for a periodic signal given in your question paper. Okay. Fourier transform for periodic signal. Particularly, the signal sketch will be available in the question paper. Some square waveform, triangular waveform. Okay, like that. So what is the exponential Fourier series of a periodic signal representation? X of t equal to summation a k e power j k omega naught t, right? Where k varies from minus infinite to infinite. Do you remember this? Exponential Fourier series representation of a periodic signal. Okay. Now apply the Fourier transform. Ft of this particular signal. Fourier transform of this particular representation. So Fourier transform of summation k equal to minus infinite to infinite ak e power jk omega naught t. Okay, the summation ak are constant. So we can rewrite this particular step by summation k equal to minus infinite to infinite ak Fourier transform of e power jk omega naught t. So what is Fourier transform of e power jk omega naught t? Fourier transform of e power minus j omega naught t is 2 pi del of omega plus omega naught. Okay, so already we solved. So 2 pi del of your result is summation k equal to minus infinite to infinite ak 2 pi del of omega minus k omega naught. Here k omega naught is there. So omega minus k omega naught. So this is the formula. Fourier transform of a periodic signal. AK 2 pi del of omega minus k omega naught. What is AK? AK is a Fourier series coefficient only. Okay. Fourier transform of a continuous time periodic signal formula. You have to use this formula only. Not integration x of t e power minus j omega t dt formula. Please remember this. AK is Fourier series coefficient. AK is Fourier series coefficient only. So what is the formula for AK? We know already 1 by t integration over the time interval x of t e power minus jk omega naught t into dt. Right? So using this formula, find AK. So in the question paper, if periodic signal given to you, you find capital T, omega naught, and then Fourier series coefficient, that is AK, correct? After compute this AK value, substitute in this formula, that is your answer. Finish it. Okay. So Fourier transform of a given periodic signal. Anyway, you have to find the exponential Fourier series coefficient AK and substitute that AK value in this formula and replace omega naught value whatever you have calculated from the given signals. That's it. Okay. So in today class, so I have covered all the properties name and definition and a few problems related with that particular properties. Okay, so all the properties are very important. In particularly, the Parseval's theorem statement as well as proof is very, very important. Okay, so Fourier transform formula, all the basic problems, properties, problems based on properties, and Fourier transform of a periodic signal, how to do it. So these are the topics we covered so far. And one more topic is pending in Fourier transform. That is representation of LTE system using differential equations. Okay. So any differential equation given, how to solve those differential equation using Fourier transform. Because we have the property differentiation in frequency domain also, differentiation in time domain also. With the help of that formula, we can able to solve the given LT system differential equation. Okay, see here, d by dt of x of t, j omega x of j omega, d by dt of power n, j omega power x of j omega. So with the help of this differentiation in time domain property, we can apply this Fourier transform for analyzing the differential equation. Okay. The differential equation is the